Alright, let's talk a bit about matrices. And what I want to give you here is an intuition behind a special type of matrices that we're going to use in Houdini, the transformation matrices. So, working with geometry usually involves using some kind of coordinate system to determine where a point is in space, usually x, y, and z coordinates. And this coordinate system is usually defined by its axis. In our case, we have this very simple system here, two-dimensional case, defined by its x-axis, extending 1 unit in x direction and 0 units in y direction, and a y-axis, extending 0 units in x direction and 1 unit in y direction. We could, for example, use the system to draw a circle with its center positioned at 0.5 and 0.5 in x and y. And to get to the center here, what we have to do is multiply the x component and the x vector. So 0.5 times 1 and 0.5 times 0, and to get to the center's y-coordinate, we do the same thing respectively with the y component here and the y-axis vector here. So 0.5 times 0 is 0, and 0.5 times 1 is 0.5. That yields this result here, which leads us to this position of the circle. But what we also could do is we could scale our y-axis by 150%, so it's now 1.5 units long and not 1. So this will result not only in our center being a bit further up at 0.75 now, but also in the points of our circle being stretched. And this is the underlying math. So for our center's x position, we take the original 0.5 and multiply it by the x-axis vector here, which results in this here. And for the y, we take the original y component of our center, which was 0.5, and multiply it with our new y-axis here, which yields this result here. And to finally get our center's vector, we add both vectors, both individual vectors for the x and the y-axis. So this results in this new center here at 0.5, 0.75. So what we basically did by scaling our y-axis of our coordinate system, we scale our geometry. But we can even have our axis pointing in any given direction. For example, in this case, we point our y-axis in the direction of 1.5, 1.5. So, using the same calculations here as previously, our center will now sit at these coordinates here, 1.25 along the x-axis, 0.75 along the y-axis, and the whole resulting geometry of our circle will be sheared. Of course, what we could also do is rotate our axis system. This involves a bit of trigonometry, cosine and sine functions, but in general we can transform our axis system. And that is kind of useful. But what has that got to do with matrices? Well, let's talk about how we can store our axis system. In our simple 2D case, we could just use two vectors for the x and the y-axis to store them. But using two variables to store one transformation and all those multiplications and additions, well, they seem kind of tedious to write out. Instead, what we use is called a row major matrix. And that's just a fancy term for saying we store individual vectors in the row of a matrix here. So this is our x and this is our y vector. And in contrast to a row major matrix where the vectors are stored horizontally, the other type of transformation matrix uses a column major system, so the vectors are stored along the vertical axis. However, forget about that. Houdini only uses row major matrices for transformations. So the matrix in our case is a 2x2 matrix, meaning it's got two members horizontally and two members vertically. It consists of 4 individual numbers, and in our case we just called it TRN for transform. The cool thing about storing our axis vectors in a matrix is that we can use Houdini's built-in math functions to transform any point using our matrix by just multiplying it. So our new position is our old points position times our transformation matrix here. It's that simple. We just multiply our points position with a transformation matrix and Houdini will take care of everything. But what about three-dimensional coordinates? Well, instead of a 2x2 matrix, we're just going to use a 3x3 matrix to store 3 three-dimensional vectors for all of our axes. So that's my x, that's my y, and that's my z-axis. So cool, you might say. Scaling works, shearing works, even rotations work. But what about translations? Well, to also store translations, we need to upgrade our matrix again, so this time to a 4x4 matrix, and this purple 4th vector here just stores the translation of our axis system, which I just moved 1 unit along the x-axis here. And to fill in the missing places in our matrix here, these 4 places, the convention goes like this. We fill the first 3 positions of the column with zeros and the last position with a 1. So just don't worry about this 1 here. It's always there. It's just a matter of encoding your translation into a 4x4 matrix and applying it correctly. So don't worry about this last column here. To demonstrate some of the basics, let's just drop down a geometry, dive in there, delete our file and drop down a pighead test geometry like this, and after that I'm just gonna append an attrib wrangle set that to run over details. And what I want to create here is a transformation matrix as a detail attribute. So there are several ways. Let's first use the hardcore way and just create 3 vectors for 3 axes and a 4th vector for translation. So let's call one x for the x-axis and set this to be along the x-axis, like this. Do the same thing for y and z. And also create a vector for the translation. In our case, set that to 0, 0, 0 to have no initial translation. Next, we're going to create our matrix. Call it trn for transform. That's working so far. And next I want to set the individual components of the matrix to my vectors. And also within our vectors, let's not forget the 4th column that we need for a 4x4 matrix. So instead of using 3-dimensional vectors, let's use 4-dimensional vectors. And add that last column to our vectors, which is 0, 0, 0, and 1, like this. Next, let's set our matrix components, and this works really similar to a vector. So trn equals, and let's use the set function to use some variables, x, y, z, and t. So that's working, and now finally let's write this out as an attribute. And the at syntax in this case is 4 for a 4x4 matrix, and 3 for a 3x3 matrix, and 2 for a 2x2 matrix. So 4 at trn for transformation matrix equals to trn, our variable. Let's highlight this node here, head to the geo spreadsheet, click on the detail attributes, and we can see our 16 components of our transformation matrix called trn have been set. Let's check by just altering some of them. So here, transformation is set to 3 along the x-axis now. Let's apply this by dropping down a point triangle, buying this in here. And what I want to do first is I want to read out my detail attribute. So again, my 4x4 matrix. Again, let's call it trn equals to the matrix that we stored as a detail on our 0 input geometry. We called it trn. And all I have to do to apply the transformations stored in that matrix now is just multiply my points position, or any position that I want to transform, with this matrix. So v at p times equal trn. That's it. And I can immediately see I translated my pig head here, and I translated it by 3 units, because in here I specified my transform to be 3 units along the x-axis. So let's get rid of that and try scaling that, maybe along the z-axis, by having the z-axis not extend 1 unit, but 3 units. So I can see now I scaled my pig head along the z-axis to be 3 times as big as previously. Also, let's shear this by moving the z-axis up a bit, so we get some shearing in here. Let's do the same thing along the y-axis and shear this a bit as well. So all kinds of weird transformations. Apart from using this set command up here to set the individual components of my matrix, I can also use the same syntax as with my vectors, but only when I use constants. So for example, I could do this, curly brackets, and within the curly brackets, I will write my individual vectors, and those of course are specified by using curly brackets again. So my x vector is this, my y-axis is this, comma, my z-axis is this, and finally my transformation vector is this. So that returns a standard, normal transformation matrix, as we are used to. Again, let's try scaling the z-axis. Yeah, scaling along the y-axis, so that works too. But this is tedious as well. So both of those methods here require you to write out lots of stuff, when all we want is a matrix that looks like this, with zeros in all the places except for this diagonal here, which is filled with ones. And this is called the identity matrix. And luckily, Houdini has a built-in function to generate this kind of matrix, an identity matrix. So let's just use that by using the ident function here. And that's just called without a parameter. So again, what we have here is our standard identity matrix that looks like this here. So to be super clear about this, applying an identity matrix as a transformation matrix to a geometry doesn't transform the geometry. Basically, what the identity matrix stands for is do not transform this geometry. Also, there are a few handy visualizers that help you figure out how your matrix is oriented. So let's highlight this here, the detail wrangle, and go into the visualizers section here. And let's drop down a visualize node here, wire this up, highlight it, and in the visualizers tab, let's set the type to marker and select axis as type, and finally set our attribute to trn, and it's a detail attribute like this. And of course this only works if I have trn stored as a point attribute for whatever reason, so maybe I found a bug here, maybe some of you know the solution to this problem, but here you see the orientation of my axis using this transformation matrix that we just created using this detail wrangle here. Let's try this scaled version here. And as soon as I uncheck normalize vectors, I can see this is the orientation of my scaled version with my y and z axis being longer than my x axis. Alright, back to my attribute wrangle here. Let's deactivate the visualizer just to make sure. Let's clean this up and let's just only use this ident function here, which we can write as one line of code here, and then we just store out our matrix as a detail attribute like this. Alright, so scaling and shearing, that works. What about rotation? Well, we could calculate those individual coordinates of the x, y, and z axis of our coordinate system individually using quite a bit of trigonometry and math. However, we can just use one of Houdini's built-in convenience function, in this case called rotate. Let's just open the help page for that. There are several versions how to call this, and what it needs is the name of a matrix to rotate and the amount, so the angle, how far it should rotate a matrix. And this version here applies only to two-dimensional matrices, because the rotation axis is always the axis perpendicular to the other two axes. However, in our case, we have a three-dimensional or even four-dimensional matrix, so we need a vector that specifies along which axis the whole matrix should rotate. Let's try that out by dropping down our rotate command. Then we want to rotate our matrix called trn. We want to rotate it around an angle, and again, when looking at the help page here, the angle must be given in radians, so instead of 0 to 360 degrees for a full rotation, this is 0 to 2 pi. So let's use just a ballpark value of 1.32 here, and finally we need to give this a vector which specifies the axis of rotation. So if we want to rotate this simply around the y-axis, let's give it the y-axis, just pointing up 1 unit along the y direction. Let's highlight our point wrangle that applies this transformation, and we can see we just rotated our pick at almost 90 degrees. Let's increase the transformation a bit, and we can see we transformed it further. Let's maybe rotate it along the x-axis instead of the y-axis. So you can see here now that's rotating along the x-axis, and we can also specify a vector that points along the x and y-axis maybe. And what you see here, this shearing that's been introduced by this rotation, is due to the fact that this vector here is not normalized anymore. So the length of this vector is bigger than 1. In our case, the square root of 2. So let's normalize this using the normalize command. And our rotation is working as expected, rotating this picket around this axis here. Let's try along the z-axis too. Okay, no shearing too. And to simplify this and make this a bit more predictable, more akin to what we used to as an artist, let's first create a variable, call this angle, and it should be equal to the radians of a float slider that we're going to specify, and let's call this float slider rotation. Create the slider here, and maybe head into the edit parameter interface, and then specify a range of maybe minus 360 to 360, so that we can specify our input angle in degrees here. The radians function converts that into radians, so instead of typing just something here, let's use this angle value here to dial in the rotation in degrees. Next, we don't want to have this rotate just around this one weird axis that we specified somewhat randomly, but we want to be able to dial in an x, y, and z rotation. So let's do that by specifying not only one angle, just copy this line here and paste it 2 times. Call this one rotation underscore y, and this one rotation underscore z, and let's call this one angle underscore x, angle underscore y, and angle underscore z. And let's change it here. So our first rotate command should rotate our whole matrix, the amount stored in angle x, and it should rotate our whole matrix around the x-axis. So 1, 0, 0, like this. Let's create all the other sliders too. We can see now this rotates around the x-axis only. The other sliders don't do much yet, but again in the parameter interface editor, let's dial in the range for the other two sliders as well. So they range from -360 to 360. To actually take into account the y and z angle rotation, let's copy this line here, paste it 2 times again, and just exchange the angle x with the angle y and angle z. And for the angle y, we want to have a rotation around the y-axis, and for the angle z, we want to rotate around the z-axis like this. So what I have now is I can rotate around the x, the y, and the z-axis. So what we built here is basically a very elaborate version of Euler angles. Let's reset our rotation, and maybe again in the parameter interface, let's call this one rotation underscore x, and also adjust its label, hit apply, accept, and adjust my CHF command here for the new slider name down here. So what if we want to scale this whole thing? Well, yes, we could create our individual vectors and store them into the matrix and manipulate the matrix directly, or again, we could use a convenience function, in our case called scale. Let's head to the help page. So this one scales the given matrix in 3 dimensions simultaneously, and x, y, and z are given by the components of the scale vector. So 2 parameters here, the matrix that we want to scale, and the vector storing the scaling factors for x, y, and z. So we want to scale our matrix called trn, and we want to scale it by a scale vector, which we have to create first. So vector scale underscore vec equals 2, and let's create an interface element for that. Call it scale and create it. So we don't see anything here in the viewport. That is because our scale is set to 0 along each axis. So let's set it to 1, and there we have our pig head back. And now we can dial in the scale along each axis here. Finally, we want to be able to move this pig head around, so to translate it, and of course, you guessed it, there's a convenience function for that called translate. Help page again, and as previously, this function has 2 arguments, the matrix that we want to translate and the amount stored as a vector. So let's translate trn by vector, which we'll call translate underscore vec, and of course we have to create that first, so vector translate underscore vec equals 2, and let's create an interface element again, call this one translate, create that, and now we can dial in the translation along the x, y, and z-axis. So these are the bare basics of creating and manipulating standard transformation matrix in VEX.